Hello and welcome to YMT215 Logic Circuits. Today we are going to discuss the first part of Chapter 3, Logic Gates and Gate Combinations. And in this part 1, we are going to discuss only Introduction to Boolean Algebra. You guys are familiar somehow with Boolean Algebra, and there are many things we have already covered related to Boolean Algebra in discrete mathematics. And also in this part, or the previous, chapters that we discussed in logic circuits. So, what is Boolean algebra itself? What's the whole idea about it, and how do we use it in logic circuits other than discrete mathematics? The idea of Boolean algebra is representing operations on variables in logical way. Meaning what? Instead of dealing with mathematics, here we deal with true and false, a type of algebra that is applicable to logic, to 0 and 1. So we have two outcomes only, either a 0 or 1, and in that case we need suitable operations to these outcomes, or what we expect as outcomes. Do we have variables? Yes, and these variables that we have represent only 0 or 1 in any case, either 0 or 1. How do we get these zeros or ones? We represent them as a location in the memory in the computer, and then we get them from that memory based on a variable. So our variable represents an action, could be possible in logic or Boolean algebra, a condition, possible also, or a data in the memory. So one of these. And ultimately it is either 1 or 0 as a value. So remember this. Okay, a variable in Boolean algebra is referred to by a letter, whatever letter. Usually we use uppercase letter. In this course we will follow an uppercase letter or a capital letter for a variable. And if we place a bar on top of the variable, let's say we have a variable a, capital letter A, and if we place a bar on top of it, means its complement. So if the value of a is 0, then a bar will be 1. This is pronounced a bar or not a. So it's up to you to say it. If you like a bar, say it's a bar. If you like to say not a, it's also fine. In some books they provide another representation for a bar. They call it a prime, or the complement of a, and in this case it is not a. Suit yourself, it's up to you, the way you say it, the way you use it. It's fine to me. In this course, use whichever you like, whichever suits you. Alright, we have something we call literal. A literal means a constant value, 0 or 1, because we don't have any other, but it's literal, it's provided the way it is, and we assign it to a variable. Alright, so what kind of operations do we have in Boolean algebra? Again, as I said, we don't have normal arithmetic operations, rather we apply our operations here on true or false, or 0 or 1 digital data, and in that case we refer to it by logical operations or logical expressions when we have those. The first one is or operation, is very similar to the addition, the normal addition in arithmetic we have. However, it is applied to logic to either 0 or 1. We have four possibilities for two only variables, and they cover for the rest. Now, what it means, for OR operation we have 0 or 0, that is 0 as an outcome, 0 or 1, that's 1 as an outcome, 1 or 0, that's 1 as an outcome, 1 or 1, that's 1 as an outcome. Now for arithmetic operation, if normal addition, 0 or 0, that's 0, fine. 0 plus 0, that's 0. 0 plus 1, that's also 1. 1 plus 0, that's 1. But 1 plus 1 is 1, 0. So we have somehow a missing here for this logical operation. We'll speak about it later on, but this is a logical operation, OR. So OR is always 1 as long as there is 1 somewhere. in the OR operation or in the ORing process. We pronounce it sometimes ORing process. It's possible, so you don't feel it is weird. It's possible. So we don't have carry here. It is just one unique outcome for this operation, and based on that we have only 0 when all inputs are zeros. Can we have more than 2 inputs? Yes, it's possible. You can have as many inputs as possible, and you OR each coincided bits together. All right. Let's take a simple example about OR operations. The operation of OR. Now, let's say we have determined the values of A, B, C, and D that make the sum term A or A bar or C or D bar equal to 0. Now, ORing these variables or their complements, it doesn't matter, will be 0 only and only if all these terms are 0. Now, if we assign A 0, that will be fine to this part, but if we assign B a 0, that will take it to 1. So what we will do, we will assign B 1 and then C 0 and D 1. What will happen? 0 or 1 bar, which is 0, or 0 or 1 bar, which is 0. That will take you back to 0. This is a simple example, shows you the process of OR or ORing. We have the multiplication, the Boolean multiplication. This is not algebra. It's not algebraic multiplication or arithmetic multiplication. Here what we have is the AND operation. ANDing of bits, we can start by 2 bits. We cannot AND 1 bit. It's not possible for us to AND 1 bit. All right, so what we need to have here is 2 inputs at least. We have to have 2 inputs minimum. We can have more than that. Let's see the outcome. How is it represented? You can directly say A, B, or A and B, or you can place sort of a dot, which is a bit thick and big like this. It's up to you, suit yourself. I personally use this representation A and B directly, right, without placing any dot, unless it is necessary. Sometimes you feel it is necessary, so just provide it if you think that there may be a confusion if you do not place it. Now, let's say for this case, 0 and 0, and in this case, if you do not provide this dot, maybe a confusion happens, like 0, 0. What do you mean? Is it 0 and 0 or 0, 0? Yeah, in that case, think about placing this dot. All right, how about the outcome or the truth table for AND? Actually, we studied it before, but let's just revise it. 0 and 0, it's a logical multiplication. That's the 0. 0 and 1, it's also logical multiplication, or Boolean. It's also 0. 1 and 0, that's 0. 1 and 1, that's 1. It's exactly coincided with the algebraic multiplication or the arithmetic multiplication we apply in our life. So, and this is a common thing in this case. All right, let's take a simple example. All right, the simple example here says determine the values of A, B, and C and D that make the production term. Sometimes we refer to it production, like Boolean production, Boolean product. Okay, A and B bar and C and D bar equal to 1. In order for us to make this expression equals to 1, or the outcome equals to 1, what we need to do is we need to maintain 1 for all terms. We need to assign A 1, B we need to assign it 0. Why? The complement of 0 is 1, C 1, D 0. So it will be 1 and 1 and 1 and 1. That's it. You will get 1 in the outcome. These are very simple, straightforward questions, just an application. All right. We have laws for Boolean algebra. These are actually the basic laws that apply for both Boolean algebra and also arithmetic, the normal arithmetic operations or algebra we have, the ordinary algebra we have. The commutative laws for addition and multiplication, and you must have remembered them by now from discrete mathematics. The associative laws for addition and multiplication, the distributive law also. Those are the most common ones. Now, you will remember what I'm saying or what I have said here when you see those. Basically, if we speak about the commutative law, that means if we say A or B, it's exactly equal to B or A. There is no difference here. The ORing process here or here is same, right? The same thing goes to ANDing. ANDing A and B is exactly equal to B and A, and it doesn't matter. Meaning what? Shuffling the inputs here doesn't change anything in the outcome or the output. For the associative law means what? We can swap the ORing process, also the ANDing process, between variables based on their own order. Let's say A or parentheses B or C. You can just swap or shuffle here in this case also. Just kick C outside, place the parentheses for A or B. That means you're ORing A or B, or you're ORing these two before ORing C. How is it represented? Now look at this. A, then it is ORed to these two before going to the second input. So the second here, this input is having B or C ORed with A, or the other way around, B or C ORed with C. This is totally fine. It's totally fine. There is no problem with shuffling or swapping them. It applies also for ANDing. So the AND process is quite similar in this case. We can change the order with no problem, and this is what we refer to by associative law. It is totally acceptable and based on, proved logic. All right. Distributive means what? Either we are distributing AND over or we are distributing OR over AND. So one of these two. Now look at this. A and B or C is distributing, or the distribution of A with AND process over OR process. What will it be? A and B or A and C. This is the distribution of AND over OR. And if you look, these are equivalent, meaning what? We are just representing here B or C first, then ANDing them with A. So A and B or C, that is equivalent to ANDing A and B, A and C, then ORing the outcome. It's equivalent. I don't say equal. Why? Again, I always highlight these things. Now look, we have only 2 gates. Here we have 3 gates. So definitely they are not equal. The processing time here is not equal to this one, but the outcome X is equal, yes. All right. Now the rules that we usually apply and have in most of the cases or applications or questions in Boolean algebra are those. We have these 12 basic rules. Try to practice them, remember them. If you OR a variable with 0, it will remain the variable the same the way it is. If you OR it with 1, then the outcome is 1. If you AND a variable with 0, the ANDing of variable and 0, the outcome is 0. And the ANDing or the AND, if you AND a variable with 1, then the outcome is the same variable, so 1 wouldn't affect it. All right. If you OR a variable with itself, then the outcome is the same variable. If you AND a variable with itself, also the outcome is the same variable. If you OR a variable with its complement, then the outcome is 1. Why? Now we have 2 possibilities for this variable, only 2 possibilities, which are 0 or 1. Its complement will have exactly the opposite. If this one is 0, this one is 1. If this one is 1, then this one is 0. Either way, the outcome will be 1. ANDing a variable with its complement is always 0, exactly what we explained here. If this one is 1, the other one is 0. If the other one is 0, then this one is 1, and the outcome in this case will remain 0. Double negation. The double negation takes us back to the same variable. Again, the outcome is equal, but the process is not. The process, we have double negation. We have 2 extra processes here. Negate for the first time, negate for the second time. So minimum of 2 negation or two NOT gates, and that takes more delay. So I always highlight this. They produce an equivalent outcome, but the process itself is not equal. Okay, here we have if we or A and B, then the outcome is A, and I will explain why in a while. If we or A bar and B, the outcome will be A or B, and I'll explain this one also. The last one, if we have A or B ANDed with A or C, then the outcome is A or BC, and as I will explain this one as well very soon. And we will have also a tutorial. This will be about the Boolean algebra. Previous chapters didn't really need tutorial. After this one we will have real tutorial about those. Now this is the realization of the process. A or 0, that's A. It's an OR gate. It doesn't matter if A is 1 or A is 0, it will remain the same as is. So if it is 1, it will remain 1. If it is 0, it will remain 0. This applies to 1. A or 1 remains 1 no matter what A. So this is exactly the rules we explain. They're proved from the gates, and you guys are familiar with these gates. We'll speak about them in more details in the next part. However, for the time being, we just apply them for these rules. And now if we are ANDing 0 with a variable, then the outcome is always 0. If we are, no matter what, the variable what, why? Because 1, 0 in an AND gate input guarantees that the output is 0. Okay. If you are ANDing with 1, then it depends on the variable itself. So if it is 0, the output is 0. If it is 1, the output is 1. Now, ORing with A, the same input, it will remain the same as the output. So A or A will be A as an output depending on the value of A. If A is 0, then the output is 0. If the value of A, or if A is 1, then the output is 1. ORing A with its complement takes you always to 1. We explained about this. I explained about it. I don't need to re-explain it again. ANDing A with itself takes you back to A. If it is 1, then the outcome is 1. If it is 0, takes you back to 0. ANDing A with its complement always takes you to 0. Why? Because if this one is 1, then this is 0. If this one is 0, then this is 1. Either case will take you to 0. Well, double negation, I said, these are not gates. We will study them separately in the next part of this chapter. However, now if you negate a variable for the first time, it goes from 0 to 1 or from 1 to 0. If you negate it the second time, it will go from 1 to 0 or from 0 to 1 depending on its value. So if we have A as 0 here, if you negate it for the first time, it goes to 1. If you negate it the second time, it will go to 0. So it goes back to the same value of A, and this is what we refer to by double negation. It's equivalent to the same input. However, the process itself is double negation. We have two gates. It's not equal to just having the input fed directly. For sure, there is a delay in these gates. All right. So let's take some examples. Let me take the pen and explain. Now, how do we have the outcome here, A? Now, there is an easy way to do it. Now, look at this. We have a distribution here of what on what, or and over or over and, or what. So if you want to take the easiest way is assuming that I have A and 1. A and 1 here in that part will take us to where? Will simply take us to the next step of taking A common from both. So if I take A common here, what will remain? 1 or B. So take A common, what will remain here? A and 1, so 1 only will remain. ANDing a variable with 1 will not change the variable will remain the same. So what will happen? 1 or B. ORing a variable with 1 is always 1. So B or 1, no matter the value of B, what? If it is 1, again, the outcome is 1. If it is 0, the outcome is 0. So this one is always 1, always 1. wouldn't change. And that takes us to A and 1. A and 1 is A, and that is how we derive A as an output in this case. And this is the equivalent in realization of gates. A can be a straight connection like this, or represented by A and B or A. Well, even though they are equivalent, but look, here we have two gates, and a way of delay, of course, it wouldn't compose the same outcome. Let's think about this one. I have an easier way. Don't look at this. I'll tell you how. Now, A or A bar and B is equal to A or B. How do we get it? It's easy. Distribute A over this end. So we have or and. A bar and B, and we have A ORed with them. Then let's distribute. How do we distribute? A or A bar, and let me try to write it. I'm not very good at typing with mouse. A, okay, or, oh, it's not going to work. My hand is really not stable with mouse, so I'll just say it by my own words. A or A bar inside parentheses, A or A bar ended with A or B. Okay. A or A bar here, first part. A or A bar is always 1. Okay. And then what will be remain? A or B, we cannot simplify it. A or B cannot be simplified. Now if you and any variable and 1, the outcome is the same variable. If you and a process with 1, also the same process. So A, here we have it inside this parenthesis I just said. This is the distribution of A over, that means ORing, A with A bar and B. All right, 1 and A or B is exactly AB. So you don't have to go all the way like this. Just distribute or over and. So it would be A or A bar and A or B. A or A bar is always 1. And what will remain? A or B ended with 1. That's like this. It's nothing. It wouldn't change anything. It would just remain A or B. Let's take another example. This is its implementation. What it shows you, like A or B is equivalent to A or A bar B. It's equivalent. It's not equal. The outcome is equal, but it's not exactly equal. The whole process is not equal. How about the last rule, number 12? How can we prove it? It's really easy. It's not hard. You just need to distribute. Distribute means what? A and A and C, A and B, B and C. So it's like just the distribution of those over the parentheses. Then try to simplify. Simplify means what? You can take A and C. What's its outcome? A and A is always A. Ending a variable with itself is always the same variable. Then what you need to do? You need to take A common here. If you take A common here, A will be multiplied by, this is of course logical multiplication or ending. It would be ended with 1 or C. When we OR 1 with any variable, it's 1. So remember, this one is always 1. We just said about it. So this one will remain as 1. Now A and 1 is always A. Now look at the same process we can do again. We can do it with A, B. We didn't touch them. We left them. Now do it the same again. A, take it common. It will remain 1 or B. This is also 1 again. So what's remaining here? A and 1, which is A or BC, and that's the outcome or the output. We will have an easier way for simplifying these expressions later on, not now, but for the time being we have to get used to those. Train yourself. I'll also create a tutorial for this where I place things similar to the simplification of those, but in more practical examples. This is the implementation. If you see the implementation and the equivalency, for sure here we have 2 gates, here we have 3. This is more complicated as an implementation, but the outcome here, x, is the same for both of them, and that's why we refer to it by equal. So it's equal as an outcome, but the idea here is not of just having an equivalency in the outcome. Also, we look into the implementation itself. For the values of a and b and c, I'll explain about them shortly. I didn't go through them now. These are truth tables, and I will give them to you a bit later on, not now. Let's just understand the Boolean algebra, and this is the end of this part. I'll create a video for the second part very soon. Until then, have a good time. Goodbye.